So in this video, we're going to show that the limit as x approaches 4 of the expression square root of x is equal to 2, okay? So looking at this is one of those simple limits where literally you just plug 4 in to x and you take the square root of 4 and you get 2. Makes sense if that's set up right, but now the difference is we are going to prove this. But before we prove this, we're going to use numerical tolerances first to kind of get ourselves in the mode of how we go about proving given limits. Okay, so what I'm going to do is I'm going to let epsilon be this fixed number 0.5. Okay, so remember epsilon is how far away, the maximum amount away I can be from my limit and the function value. So my error in essence is a maximum of 0.5. So the question is, how close to 4, so how close do we have to get x to 4 in order that y will be within 0.5 of the answer 2? Okay? So how do we do this? I'm going to set up the inequality. So y is stuck between the limit minus epsilon and the limit plus epsilon. As we talked about in our video, we have our bounds here. We're stuck between minus epsilon and plus epsilon. That's where the y value is stuck between. Okay. So what does that tell me? For an epsilon equal to 0.5 and a limit L equal to 2, I'm going to substitute L with 2 and epsilon with 0.5. So I have 2 minus 0.5 and then I have 2 plus 0.5. And so if I simplify this, I get 1.5 and 2.5 for my extremes of what y could be. Now, what I'm going to do is I'm going to replace the y with my function, okay? Because remember, y equals the square root of x here. That's my output. And so I'll replace this y with the square root of x, okay? And now what am I trying to do? I'm trying to get my x by itself because I want to know how close does 4 have to be to x, right? So I'm going to square this square root to get rid of the radical. And so if I square the middle, I get to square everything. And so I get 1.5 squared gets me 2.25 and 2.5 squared gets me 6.25. So my x, what this is telling me is that the x values range from 2.25 to 6.25. And as long as we're within that range, then we'll be within 1/2 of my true limit of 2. Okay? So, what do I do here? Well, I'm going to take the x value, okay, the x value, and then subtract it from this lower c here, the 2.25, and I get 1.75 on this side, okay? And then from this one, I take the c value, and I subtract from that lower x value, right? So what is this going to do? It's going to get me 2.25 here. So I have a delta here, and I have a delta here, okay? So the question becomes, what is the desired x tolerance? Okay, so which one do we pick? Well, I want to have an interval that is symmetric, okay? So the interval of x values is symmetric, right? And you saw from this picture that we had up here, if we just picked the delta 1 and then the delta 2, that this right here where that limit is not in the center of that interval. We need it to be symmetric. So how do we do this? Well, we do this by picking the smaller of the two deltas, and then we get this symmetric interval going on here. Okay? So let's do that. So x is going to be 4 minus delta and 4 plus delta. Okay, by definition. All right. Now, what is delta? Delta needs to be the smaller of the two. Which one is smaller? That's the 1.75. Okay. Therefore, what do we know? Given some epsilon equal to 1/2, we have found a delta that's less than 1.75, such that whenever x is within delta units of 4, okay, so when we're within delta units of 4, we've got our delta equal to 1.75, then y is within epsilon units of 2, okay? So this shows us how to do it for some particular given epsilon value, okay? We can find a delta, okay, such that this following statement is true. Now, what's going to change here? Instead of having some fixed epsilon equal to 0.5, I'm going to make epsilon arbitrary. And not only is it arbitrary, but it's positive and arbitrary, meaning that it can get as small as possible without being 0 or negative. Okay? And what this does is this allows me to get as close to the true limit as I possibly can. Therefore, we can prove that the limit equals that L value. Okay? So how do we do this? We start by assuming that by assuming that y equals the square root of x is within epsilon units of 2. So how do I show that? I literally write out the definition. What does the definition say? This is true, okay? So I'll write out my definition. Okay, so the definition, f of x minus L in absolute value is less than epsilon. My f of x here is my y value. Minus L, the limit was equal to 2. That's what we had here for this problem. The limit was 2. This was the y value, right? Okay, and that's less than epsilon. See how this is exactly the definition right here. Okay, so we start with the end result. We're doing scratch work in red and purple here, and then we'll get to the answer. Okay, but you need the scratch work to get to the answer. I use algebra to separate this out with the absolute value. Absolute value is distance, so that means you think about a number line. If absolute value is distance from 0, we're saying that it's less than epsilon this way, then that means we're at a distance of epsilon negative that way. Okay, so that's how that works, why there's a negative 1 on this side and a positive 1 on that side. Okay, and so what I'm going to do here is I'm going to replace the y with the square root of x, okay, because y equals square root of x here. And so now what I'm going to do is I'm going to solve for x. How do I do that? I'm going to add 2 to both sides. And so I get 2 minus epsilon and 2 plus epsilon. Okay. Now to get x by itself, what do I need to do with the square root of x? I need to square it. So I'm going to square everything. And so whenever I square everything, I'm going to need to multiply this out. And so if you want to write it out, that's fine. 2 minus epsilon times 2 minus epsilon, and do the FOIL, right? And do it on both sides, your FOIL. And what do you get? You get 4 minus 4 epsilon plus epsilon squared, and then 4 plus 4 epsilon plus epsilon squared, okay? Now, what you have to remember is this. We're looking for something that's set up so that I have 4 and then minus something, and then 4 and I have plus something. Okay, that's the setup for this particular one, since my limit is as x approaches 4. Okay, and if you think about this piece right here that which we're working with, if you solve this for x, you know, that's where you get your delta and your c playing in there. Okay, so what do we need? I need a 4 minus something, and then I need a 4 plus something. Okay, so I put those in different colors so that you can see. All I did was I added parentheses there. Now if you add parentheses here, you have to be careful because that's a plus. So in here I made it minus because minus a minus distributes to a positive. So you got to be careful when you put that. Everything in the parentheses gets that negative multiplier on it. Okay, so very tricky there. All right, so the desired form is 4 minus something and then 4 plus something. Okay, so the question is, what is that something? That something is our delta. Okay, that something is our delta. Now, let delta be what? It has to be the minimum of the two things that we've seen here. So those are those two things there. Why do I pick the minimum? So that I require it to be within the band. Just like I picked the minimum delta here, delta 1 and not delta 2, because had I picked delta 2, then my delta 2 would have went outside the green band up there. Okay? So you're trying to pick the minimum delta so that you get mapped within the same inside band there. Same reason that we picked the minimum, we picked the smaller of this delta 1 and that delta 2 there. We always pick the minimum, okay? Now, how do I find the minimum here? It's the minimum of these two things. Well, guess what? When I look at these two things, okay, this and this are the same, all right? However, when I square a number, it becomes positive. So subtracting a positive number versus adding a positive number, guess what? Subtracting that positive number is going to make that number the smaller of the two. So that's why this piece is the minimum here, okay? So kind of a weird way to think about it, but these two pieces are the same, but it's like I'm literally saying, okay, those are the same, but then I'm going to subtract a part from that number, and I'm going to add that same thing here. Well, guess what? When you subtract it, that makes that number overall a minimum, a smaller number. So all this thing is saying is that I'm literally taking the minimum of the two things in my little curly brackets. So since epsilon is positive, okay, since it's arbitrarily small and it's positive, then we choose this to be our minimum value, okay? And if you're kind of fuzzy on this, you can check yourself, plug in 0.5, see what you get there. If you plug in 0.5, kind of like what we assumed up here, right? I plugged in 0.5, I got a delta of 1.75, right? Okay, I plug in 0.5 here, and I get the smaller delta of 1.75 there. Okay, so it turns out if you plug in 0.5 into this, you get that 1.75. So that's what we're looking for, the smaller of the two deltas. So we're kind of making connections here, all right? So now I'm starting with my proof at this point, okay? So I start with the definition, Okay, so what is it? I want x minus c to be less than delta. C here is 4. I'm limiting to 4. That's the c value. Okay. So x minus 4 is less than delta. Let's use algebra to simplify this. All right, now look. Delta, we said, was 4 minus epsilon squared right here, okay? So 4 minus epsilon squared is what it's less than, okay? So we're okay here. And, you know, technically, if you wanted to get kind of cuckoo with it, technically what's going on is this right here. You got delta, which is less than that. But guess what transitive property works here? So that's why I can get around saying that. Okay, so now I'm going to use my algebra here, and I'm going to do my inequality. So I have a positive and a negative on the two sides. So I have the positive one and the negative one. All right. Now, what I'm going to do, so I'm going to add 4 to all sides. Okay, now, before I get to that, though, I want this thing to be symmetric, okay? So if I were to go through here, this is not the same as that is there, is it? Okay? But what do we know? We know that this piece and this piece are the same, and that this piece is bigger, right? So what I can do is I can rewrite this. I can make this the big piece right here, okay? So I know this to be true because this thing is smaller than that thing right there. Okay, if you think about it, 4 minus epsilon squared, since epsilon is positive, then 4 plus epsilon squared is bigger. Okay, since you're adding a positive squared number, that's where that inequality comes from. All right, so that way, the reason we're doing this is because we literally want this to match up. Okay, if we don't do that, then we're not going to get that thing to match up there. Okay, that's why we work our scratch work first, so that we can turn the work around and go back this way. Okay, so we literally work it backwards, and now we work it forwards. That's why we do our scratch work first. Okay, so we got that. Now we're going to add 4 to all 3 pieces. Okay, and when I do that, I get x is stuck between this 4 plus 4 epsilon plus epsilon squared and 4 minus 4 epsilon plus epsilon squared. Why is this important? Because that's exactly that line right there. All right, you see how we had to manipulate the numbers to be like this, so that's why we had to take this extra step here to get to this point right there. Okay. Now, after that, I can factor it, and I look really, really smart here because that piece right there, the next step in the line is right there, okay? So remember, guys, we're literally going down this way is going back up this way over here. It's literally going in the opposite direction. So now we know that this and this come from right here, okay? What is the next step? Here, square root it. And so I'm going to square root it. And when I square root it, I get back to this line, matches that line, okay? And now what do I have? This and this. So I subtracted 2 from everything. And now I get right back to where I started, as desired. Okay? So sometimes these problems, in fact, this is how you're going to set it up. Always start your scratch work with what you want, and then work down to some magical delta that you pick. And once you get that magical delta that you picked, then you take that information and turn it around. And you start with this part, okay? And then you throw in your magical delta. And then, to the reader who's reading this, it's like, where in the world did they get that 4 epsilon minus epsilon squared? That seems random. And then all of a sudden, you're running through these lines and you're like, oh, this matches with this. Oh, that matches with that. Oh, this matches with this. Huh, that matches with that. Here we go. Here we go. It's a lot easier when you're working through your scratch work and going down that direction, okay, than trying to go backwards whenever you write the formal proof. It's impossible to start with this magical thing doing it all in your head, okay? Very, very challenging. So we do the scratch work first, and then we write it in the reverse order to get this part. Okay, so this is as desired. Therefore, given any epsilon greater than 0, choose delta equal to 4 epsilon minus epsilon squared. Then, if the absolute value of x minus 4 is less than delta, and we have the possibility that x is not equal to 4 itself, one other way you can write that is if you did something like this here. You said that this was like that. That's another way to get this in there. Okay, I think that's so your book does it like this. Other textbooks, they write it like this. Okay, either way is fine. I just did it that way because that's what your book does. Then what do we say? Absolute value of f of x minus the distance between the function value and the limit is less than epsilon. But guess what? We made epsilon arbitrarily small and positive. Therefore, that number can be as small as you want it to be. So what does that tell me? That tells me that the limit as x approaches 4 of the square root of x is actually equal to the number 2. Okay? So very powerful right there. And so it's a whole lot to take in. I know it's a whole lot to take in. I wanted to zoom out to give you a whole shot of everything here. And then you can see a whole view of this part up here. But this is how we use the definition of a limit to prove that a limit actually is equal to this number here. Okay?